downtown Qingdao. And then we will go to the Hisense company. We'll have a tour, and we will have a banquet after this. So with this, let us welcome Professor Yu Chen, and he'll give the second part of the lecture.
Among these sections, we have reviewed two types of lasers that are most likely used in display systems. So we reviewed semiconductor lasers and the solid laser from three perspectives: the pumping mechanism, laser material, and cavity structure. Based on these three perspectives, we can help us understand why the semiconductor laser is the most popular laser, has the widest applications. Because first of all, you have a very simplest pumping scheme. We can just use apply voltage because the simply are pin junctions. We can get a very efficient conversion from electricity to laser optical powers. And also another important from material point of view, because semiconductor material is for the lasers made by the similar or same technology and equipment by the integrated electronics, so it can be made, can achieve the economics of scale, and also we all know integrated electronics can be made very small. All these advantages make the semiconductor laser the most popular one choice for many applications. But from material side, only problem is we now only can find efficient emission from infrared, red, and also relatively good for blue. But for green, we still have a problem. And intrinsically, from laser cavity point of view, semiconductor laser, we can have a lot of structure to engineer its longitudinal mode. But its transverse mode is have a very good, very large numerical aperture. So its divergence angle is large. This is one of drawback for semiconductor lasers. So based on these two drawbacks, one is we do not have efficient emission for green, so we have to go to the nonlinear optics with to do the frequency doubling to help to convert the infrared wavelengths to the green wavelengths, and also even have many benefits, advantage of semiconductor because its transfer mode is not good enough. Is light laser beam directly out of laser dot is not good enough to match the requirement for nonlinear optics. So we'll instead of use the laser dot directly pumping a nonlinear optical crystal, we use it to pump the solid laser first. Then we use light laser beam out of solid laser to match the requirement from nonlinear optics. So this nonlinear solid state laser can work as a mode converter, both spatially like a mode profile and spectrally, because the bandwidth of the solid laser is much narrower than that of the semiconductor lasers. So in today's lecture, we'll go through all these more details, how to make this actual laser structure used in display systems. And to do that, first we need to go through some basics of nonlinear optics. In this morning, Professor Chen has gave a very wonderful discussion about the same subject. Now, which will give kind of quick go through some maybe there is some overlap of the content, but from our point of view, is more emphasis on the nonlinear crystal application into the device, not the material itself. So we will quickly go through this kind of basic, like Professor Chen has introduced, to get the frequency generation. Now here we are interested in the second order susceptibility. So once we have a second order susceptibility, that probably say that if we have a electrical magnetic field with two frequency components, if we put this term into here, then we get a new frequency generation. We can get its double frequency and summation frequencies and also difference frequencies. For our applications, we'll focus on these two. Primarily focus on this double frequency doubling, but also sometimes we cannot get rid of it. So this frequency summation will cause our trouble. So we also need to discuss this frequency summation part. This is a graphical illustration how this symmetrical harmonic generation work. For example, if we apply sinusoidal electrical field, if the polarization is linear, the generated polarization will be has kind of same shape with the same frequency. If the polarization include the second terms, then for the sinusoidal shape we cannot get exactly sinusoidal shape, but this new generated polarization can be decomposed to two components. One is a fundamental frequency component, another is a second harmonic wave. And naturally, to get efficiently second harmonic generation, we need a strong optical intensity. Like Professor Chen has shown here, before the invention of the lasers, the light intensity is not enough for us to get a significant the second order nonlinear effect. Besides this strong intensity, we also need the phase match conditions. Simply say, here we have graphically illustration what this phase match condition means. If we have a pumping light wave incident to the nonlinear optical crystal, it will generate a second harmonic wave at the very beginning and until very end. For the second harmonic wave generated at the very beginning and the end have a constructively interference. They can constructively add together. We need the fundamental wave and the second harmonic wave propagate at the same speed. So this is required. That this is what this phase match condition means. Because this dispergency and birefringency makes this possible, then we can find the pair of wavelengths that have a refract index for extraordinary wave at the fundamental frequency equal to the ordinary wave at the fundamental frequencies. So the basic way to implement the phase match condition is use birefringency materials. But use this kind of scheme to phase match, we have a lot of limitations. First of all, there is not so many materials we can work with have a right frequency for many applications. So we are pretty much work with what literature offer. So the suitable wavelength is very limited. So people will try to kind of find different ways to stretch the workable wavelength. For example, we can, instead of use the polarization along the optical axis, we can tune the angle a little bit, and also we can change the temperature of the nonlinear crystals. By these two means, we can extend the wavelength range for the applicable nonlinear optical frequency doubling. But the problem with this scheme is, if we can tune the angles, we've got so-called Wolkoff phenomena, which means the wave propagation, the phase propagation direction is different from the direction of the energy propagation. They will have some consequences for device design. For example, if we have the Gaussian beam at the very beginning, after a propagation at distance, this Gaussian beam will diverge, and its shape won't be a Gaussian beam. More severely, this optical intensity will become will be reduced. So this is not good for the high efficiency nonlinear focused doubling. So, because even though people have been working on this birefringent material for many years, but because its limitations, so people always try to come up some new ideas. Actually, one of these ideas is quasi face match skins. Actually, this is not a new idea because this quasi face match skin has been proposed several 10 years ago, but because the technology to implement this face matching skin is not well developed until very recently. So now we use the phaser representation to explain how this quasi-face match work. First of all, if we have a birefringent face match cases, because the wavelengths always kind of match the phase condition. The second harmonic wave generated in one region will have a kind of same frequency, same phase with the generated at its neighbor regions. As a result, the accumulation of all this second harmonic wave will be kind of along a straight line in this phaser representations. But if the phase match is not matched exactly, then the second harmonic wave generated one region will have a phase difference from that generated its neighboring regions. If we add this together, it will go a circular way. In the end, we might end up, let's say, no second harmonic generation at all. But the idea is if just at the half circle, we introduce the pi phase shift, then this phaser will turn a direction. In that, they can eventually accumulate a sizable second harmonic generations. This is the basic idea of a quasi-phase match. Like we said, this idea has been there for many years, but the technology is not there to implement it. How to, let's say, introduce the pi phase shift? The simplest way is to change the sign of nonlinear optical coefficient. So, for example, we have a layer of nonlinear optics at the sorry, I need to add. Say this coherent frequency. What coherent length is means the thickness of nonlinear optics crystal where we reach this half circle. So every coherent length we rotate the material to 180 degrees. Then we will kind of say change the sign of nonlinear optical coefficient. But if we calculate, we found that the coherent length is at a level few micron. So it's not very easy to do manufacturally. But recently, this can say called empirical technology will become more and more mature. So I believe in tomorrow, Professor Su will have a detailed discussions about how this this technology works and is a physical basis. Here we just more focused on its implication on the device performance. Once we have this quasi-phase match technology compared to the birefringent phase matches, its efficiency, if compared to that, we say same value of nonlinear optical coefficient, then the efficiency of the quasi-phase match will be less than the birefringent phase match schemes, because we can see, as we say here, this birefringent phase match is kind of directly up to as a line, but for this quasi-phase matches is going like a circle, so it's not as efficient. But another important thing is, if we use the quasi-phase match techniques, we do not need to work with the bifrequency, first ordinary polarization and extraordinary polarization, two principal optical axes. We can work with the large nonlinear coefficients along this so-called D33. So we can get a second harmonic generation for the same polarization. And also important thing is now we can engineer the wavelengths because the suitable wavelengths for this phase match condition will be much larger than the range of the birefringent cases. And also for birefringent cases, we only when the polarization is along the say first or say optical principal axis, you will have a so-called non-critical phase match. Non-critical phase match means once we got the nonlinear crystals, is when we have external distributions, the parameter and the device performance will kind of deviate from the design principle. But if you got a stable non-critical match, the operator say is very tolerant with all this kind of dispersion. So in other words, especially from this product point of view, we'll get a very stable device performance and also a higher yield for the production. This is very important for any technology to get really cheap and get to the consumer product like we are doing for our research. And so far we have kind of focused on the phase match conditions. And actually we also said to obtain the high efficiency of frequency W, we need a high intensity of optical light beams. But here we have a kind of problem with this. In order to get a high intensity of optical beams, we would like to focus the light wave in a very small area. But by the nature of diffraction, if we focus the light beam to a very small area, its diffraction will become larger. So from a device point of view, we need optimize this device sizes to try to get the maximum conversion efficiency. Another way to fundamentally to get rid of this kind of compromise is use a waveguide structure. Because use waveguide structure, we can have a light profile unchanged over a very long distance. But we might know because this, of course, this waveguide structure now have a lot of intensive research going on in this area. But I probably would like to point out because we are doing more on the product side, a little bit caution about this kind of technology because we know waveguide technology usually work if you have can integrate a lot of device onto the same technology platform. This is why integrated circuit, electronic circuit, becomes probably the most successful technology platform we have, human being probably ever developed. But for optical cases, we always have a problem to integrate it, especially molecularly, oscillatorically integrate everything onto the same technology same material platform. So if we cannot integrate, for example, the laser and this nonlinear optics on the same platform, it will cause a lot of connection problems, package problems. But of course, we should we should emphasize this one, open up kind of new potential, new possibility for to get a higher, nonlinear or optical efficiency. So now I would like to make a few kind of general comments about this nonlinear optics. The one thing is about this bandwidth. no matter we use the Birefringent scheme or use Quasi phase magic schemes, intrinsically, because nonlinear optical efficiency, this value is very small, so we have to accumulate the second harmonic wave over a very long distance. If you know the nature of the any wave, if you have to the wave over long distance have an interference naturally, only very, very narrow band of wavelengths can satisfy this condition. So as a result, the bandwidth for nonlinear optics is about 1 angstrom. If for some applications, like if you do some measurement, you want to very high coherent light, this is actually is a kind of pleasant, is a good. But for laser applications, we have a, let's say, sparkle problem. For sparkle, to reduce the sparkle, we want the bandwidth a little bit larger. So fundamentally, this is a kind of a problem for this nonlinear optics. If we can say increase this this bandwidth several order of different, say, for example, double or maybe even just 1 nanometer, this laser sparkle will be greatly reduced. And also, of course, like we said, now have a lot of people doing this periodic polling materials. Hopefully, it can this one can give more stable performance. And also, last thing, very important is we need kind of low-cost solutions. Now, after this preparation for the second the nonlinear optics, let's go to the nonlinear frequency-based conversion-based laser structures. There is 3 basic configurations to do frequency doubling for the visible wavelengths. One is directly use the laser dot to pump nonlinear optical crystal. Another one is, another two is we put this nonlinear crystal into the cavity. Then there is 2 ways. One is to do the one is have a separate cavity for the nonlinear crystal and the laser crystals. And another configuration is put this 2 structure into 1 cavities. We'll go to the details of these 3 structures. First of all, is the simplest structure. Just simply put the laser dot and nonlinear crystal together. This kind of configuration has obviously advantages is this has a special simplicity, very simple structure-wise, and also we know the modulation for a semiconductor laser dot is very easy. So we can, if we want to modulate the green and blue light, we can simply modulate the infrared lasers. But for most applications, this kind of configuration won't satisfy all the specs. But it is a good tool for us to, as a starting point, to start this nonlinear optical conversion. It can help us to understand other physics. The first implementation of this single path structure is use the so-called gain-guided lasers. At the very early stage of the development, because the limitation of the technology, we cannot get a very good optical guide for semiconductor lasers. What we can grow is for the semiconductor, we only can grow, say, uniform materials layer by layer. Transversely, we cannot do too much. So, at a very early stage semiconductor lasers, they were gain-guided lasers. The gain-guided lasers, they only have a guided waveguide mechanism along the vertical direction, because the vertical direction we have kind of consist of different layers. Different layers have a different refract index. By this way, we can have a kind of index guided waveguide along vertical direction. But along the say horizontal direction, we do not have really waveguide. What we have just have a say injection current. If you study this interaction between light and matters, you know once material have optical gain or loss based on KK relationship, its refractive index will be modified. So by this way, by current injection, by introduce optical gain, we can get the refractive index of this distribution along the vertical direction. In the end, we can get a kind of a weakly guided waveguide. But the problem with this laser is because this gain guided mechanism, the wavefront is not kind of flat planar, it's a kind of curved waveguide. What this means is if you introduce astigmatism. This means if we give a kind of vertical cut and horizontal cut, look at the wave distribution, we found it's focus point at different locations. This will cost a lot of trouble to design the optics to kind of focus all this into the nonlinear optical crystal. So, but after people have a really index guided material waveguide, so we can have a say index guided material for individual waveguide very for individually we can have a say very nice beam profile, but to achieve the optical intensity required for nonlinear optics, the one unit of semiconductor usually is not enough. We need an array of waveguide. So, when we put an array of waveguide, one problem we might encounter is if the distance between neighboring waveguide is not far enough, the optical wave, the mode of the individual waveguide will kind of overlap with each other. They will copulate with each other. At the end, instead of getting many individual small optical field, we get a kind of super mode added together. This super mode have a problem. If you look at its far field patterns, they have a two loop. What does it mean? This two loops means that output laser beams will propagate along two directions. This naturally can see. The two directions is difficult to focus the light beam propagate along two directions. So people have kind of try very hard to come up with high power semiconductor lasers, but try a lot of new ideas. But a lot of them is kind of say not very practical. Recently, some people are working on some new structure called angular gratings. This one looks like a little bit, say, have some kind of reasonable feasibility, have a potential to become a kind of real devices. I don't want to go to the kind of detailed discussion about the waveguide structure of this structure. This one, one thing we quite like to say, for most of light waveguide, we are usually, to make the things simple, all this electrical optical field, actually, all of them are kind of three-dimensional, but for most of waveguide, we can separately, say, kind of decouple it from into a two-dimensional field distribution plus one-dimensional distribution. So we can reduce the three-dimensional problem into 2D plus 1Ds. But here, say, this is why we have normally we have a kind of longitudinal mode as transverse mode. For this structure, this kind of transverse mode and the longitudinal mode, the dimension is not of a conventional one. What we are more interested in is not how it gets this kind of mode structure, say, kind of waveguide mechanism. What we want to know is mode properties. Here, this mode in this angled diffraction is a kind of leaky mode. If you studied the optical waveguide, you will find both conceptually and mathematically the leaky mode is the most intriguing ones. So this waveguide will give leaky mode. Here, one selecting feature is this fundamental mode have a two-fold of degeneracy. So in other words, you will have a two lowest loss mode for this structure. And each of this mode will have can be viewed have a two components. One is say plus theta component, another is minus theta component. The total field will be a superposition of this two degenerate mode. At the right some positions will find this superposition of the two Leo mode will give us the optical field only include either plus theta component or minus theta component. This is a very good feature for the semiconductor laser. What does it mean? Like we said, this in order to get a large power out of semiconductor, what we got is a two loop. Then we'll say that light beam is propagated two directions. If we only have a one angle component, the output will be just along one direction. So, and also its mode distribution is very good. It's almost close to the Gaussian distributions. So, this one probably have some promise to really reach some high power of semiconductor lasers. And also another one scheme is kind of more popular is to get the high power of pumping laser light power. Is because we know the problem with this high power semiconductor lasers is we want to achieve two things, which usually sometimes, at least sometimes, is against each other. One is we want a very good quality of beam, and also we want the very high power. This is very difficult, very demanding for semiconductor technology. If we use and divide and conquer strategy, first of all, we just design some lasers with very low optical power, but its beam quality is very, very good. Then we design another amplifier, use semiconductor technology. This one, the solely function for this port, just amplify the light, so we can separate the problem, so we can get the small lasers, but with good beam qualities. In the end, we amplify it. Then we use this output to pump the nonlinear optics, optical crystals. And also, if the amplifier and the laser all both made by the semiconductor material, you can more or less integrate them together to get integrated devices.
So this seems to be a good time to have a break, but before the break, let's see if there are some questions to Professor Chen. Are there questions? Yes.
How you achieve the coherent phase matching condition?
Sorry?
How you achieve this coherent phase matching condition with crystal?
Phase matching condition.
Yeah. How we can achieve it? I mean, in design point of view, you told that whenever the wave passes through the crystal, it has to be having the phase matching inside.
Yeah.
So if it is not phase match, then at the output there will be no SSL, no frequency generation. So how we will achieve it?
Like we. Okay, sorry.
Yeah.
If you say use the Birefringent, you just use this graph to pick up this one.
No, just.
And also.
Yeah, this one.
This one actually
yeah.
you do not have much limitation. You can choose your one, then you design your coherent lens like that. So for different let's say wavelengths, you just choose and make your material layer the coherent lens different, then you can choose.
Are there more questions? If not, let us thank Professor. And we will reconvene in 10 minutes.
This is connected to this computer. I want to insert a call, a phone call in this computer. Receiver, phone call. Yes. I want to insert a telephone number for the internet. Okay. Can I send this email and it will take a couple of minutes. Okay. One four. Maybe concave. Cannot. Is it maybe it's the local internet? No, local one. Yeah. Oh.
Higher optical power of the semiconductor laser as high as possible. But if we say, when we look, say we put a laser and a nonlinear crystal together, actually if we put two components together, we got a system. So in other words, in your have a system, you should have a kind of system perspective. In a single phase configuration, is kind of ask the semiconductor laser bear all the burden. So it's not kind of good way to design things. So we should kind of add some components to from system point of view. So if we say to improve the overall performance. Of course, one thing you can do is improve the quality of the nonlinear materials. And another thing we can do is actually add, cavity for the nonlinear optical crystals. Once you have a, why we say there are two reasons to add the cavity. You know, in a single pass configurations, the fundamental mode just propagated through the nonlinear material once. There are still a lot of leftover of the unused powers of fundamental mode. So naturally, you want, for example, add a mirror to reflect the unused fundamental powers. And if we add the cavity mirror this side from the cavity, then the unused fundamental power will kind of get inside the cavity many times in and will make much better use of the fundamental or pumping power. Actually, when you have a cavity, you will get the interference from different trips. The intensity of the optical power inside the cavity can be made much larger than the input optical power. So if you use the cavity structures, then you don't need the very high power of semiconductor laser. You only use a low or moderate level of the semiconductor laser to achieve same efficiency of producing W. So for this resonator, this cavity, we have a different type of structure. The simplest one is called standing wave structures. The problem with this standing wave structure is the light wave propagated from both directions. It is very difficult to get out of the second harmonic wave for two different directions. And also, there will have some reflection from this side. This reflection will cause instability for the pumping lasers. So in most of applications, we'll use ring configurations. For ring configuration, we can see the light will always propagate along one direction. So it's much easier to get output with light laser beams. And also for from the light propagation point of view, this ring resonator is more tolerant, more accommodated, so to the not insensitive to mismatch. So it will from product point of view, it's also will give more yield. And one drawback for this run configuration is it could have a astigmatism. So here we have calculated the ratio of the optical power inside the cavity over the input cavity input powers. First of all, we can see that this ratio can be reached as high as 100 times compared to the input pumping powers. And also, we can what we plot here is this power ratio over the reflectivity of the one mirror, and for three values of the second mirrors. From this graph, we can see first thing is when the reflectivity of two mirrors are equal, the ratio reaches the maximum. This is kind of equivalent to if you have studied the microwave circuit, you found this is exactly what happened when you have an impedance match for microwave circuit. When this impedance match happens, condition is matched, the reflect field by the resonator will become zero. So this is why all the optical field will be concentrated inside the cavity. And also we noticed is if the reflectivity of the both arrow is higher, then we can achieve very high accumulation inside the cavity. This is both good news and bad news. The good news is we can achieve really high power accumulation inside the cavity. And the bad news is we need very high reflectivity for both mirrors. What this high reflectivity means? That means when the light wave is reflected by the mirror, it will experience very tiny portion of loss. So that means after many rounds of the propagations, the light wave will still have a considerable portions. So that means the interference inside the cavity of the optical field is coming from kind of multiple beams. As a result, naturally, its bandwidth will be very, very large. The bandwidth here is for this normal size, typical size of the nonlinear optical crystal is like a millimeter. So at this millimeter, the bandwidth is very, very narrow. It's about 0.0 picometers. And also, for this level of bandwidth, it's very difficult because we know in this kind of configuration we have a two cavity, one for laser crystal, another for the nonlinear optical crystals. These two resonators have a two set of modes, so it's very difficult to align these two modes, this wavelength position exactly to each other. So and also because different cavity have a different set of mode. If you even more difficult to align all this multi-mode together. So they will cause two problems. Either is normally the solid laser have more than one mode. If we do not use kind of other single filters, make it a single mode operations, we'll waste some other mode. Only can one mode align with this mode in nonlinear optical cavities. So this is we'll have a lot of very difficult problem to align the mode of for the resonator-enhanced configurations. People have developed various technology to lock this two frequency together. For example, there are some electronic lock technology. Basically, you found some reference frequency and establish the error signals and provide feedback to. There are different ways in how to actually implement this kind of mechanism. And also, you can find that they use optical locking to inject some reference frequency into the either laser cavity or resonant cavity to lock or this frequency into one particular values. And also, another difficulty is because the laser we are working with is a high power laser. They will generate a lot of heat. The heat will change the temperature of the nonlinear optical crystal. When the temperature changes, its wavelength is the phase match wavelength will shift. So this will also need good thermal management to truly align this frequency of different frequency cavity together. So this kind of structure, even people are now still working on, probably from product point of view, they still have a lot of things to do because it is too sensitive in terms of frequency. This is one example from the Panasonic. They have one cavity for the nonlinear optical material. The material used here is a periodical poly mislabate, and also they have another cavity for pumping lasers. Here, the laser pumping laser used is not solid laser, is e-turbine doped fiber lasers. For these fiber lasers, the cavity is used in here is using the fiber bracket grating as a refractor to form the cavity. Why they choose the fiber laser instead of solid laser. One reason is probably because for this setup, they will kind of from thermal point of view, the nonlinear optics is in one place and the gain median is another. And also definitely we need a solid laser, semiconductor laser to pump these fiber lasers. The pumping source will be in another locations. So this three heat generator is not kind of separately. So it's much easier to handle the heat. This is why this setup probably give a very highest output power for this green generation up so far. And but of course, the drawback for this setup is once you use fiber lasers, the size of the device will become very large. So it will limit the use in the let's say display system. If you have a very large light sources, you have let's say do not have a lot of space left for other components. Parallel to the is Resonator-enhanced cavity structures. Another structure is put both lattice crystal and the nonlinear crystal into the one cavity. In this kind of configurations, we have a benefit of the same benefit of the Resonator-enhanced structure because the nonlinear optical crystal is inside the cavity. The optical field of the fundamental mode will be much higher than the field in the outside the cavity. And also because we only have one cavity, the mode we only have one set of modes. We do not have a mode alignment problem. And another benefit is since we have only one cavities, the device will be made very compact. We'll get very small devices. When the people first made this kind of structure called intracavity structures, when people first made this intracavity laser structures, what they found for if the mode cavity have a multi-mode structure. For the multi-mode structure, they found the single out of single is looks like this, such a messy, very messy. Because for most by common sense, if we have multiple operations, we know we might not get stable operation like in that case you have a single mode operation, but won't be like as messy as noisy like this. This originally this picture laser structure is made of KTP. When people do that experiment, without KTP, without nonlinear optical crystals, the output is very stable. So after we add this nonlinear crystal into the cavity, the signal become very lossy. So obviously this noise is come to the because the presence of the nonlinear optical crystal. So to understand this phenomenon, we first simplify the mode operations. We add some filters to limit the mode into the two mode cases. So when the laser only have two modes, what we found is the output of two mode is exactly outphase with each other. Because this two mode, there is no kind of coupling between these two. We should expect this two mode will operate independently. Here, what clearly shows this two mode is a kind of closely dependent on each other. So, after carefully studies, people found when we do this, when this say laser cavity have two modes, we will have a doubles of frequency 1 and frequency 2. But also, we could have the some frequency mixing. That means we still have a frequency at the frequency 1 plus frequency 2. So just because what we hope for is a second harmonic generation, just the frequency doubling. What we actually get is, besides the frequency doubling, we also get the summation mixing between the frequency 1 and frequency 2. Because this summation mixing, we cut this mode 1 and mode 2 are coupled with each other. For example, when this mode 2 get lazy, it will introduce a lot of loss to the mode 1 through the some frequency mixing. As a result, we bring the mode 1 down. So turn the mode 1 off. And afterward, this mode 1 will accumulate enough gain. It will turn on again. Then it will introduce the large loss to mode 1, 2 through the same frequency mixing. So this process will repeat itself. So this is why we get this kind of interlocked output. Now, right side, we have more details to say behaviors of the loss and the gain, and the gains. So, to make this intercavity work, obviously we need to deal with this phenomena we call the green barriers. The simplest solution is use many modes. For example, if we design laser cavity have over 100 modes, in that cases, the mode, all this mode will be weakly kind of coupled through some frequency mixing. If all these modes are weakly coupled together, then no one can single out. We won't find any kind of spike behaviors. So everybody will kind of equal. Nobody can stand out. For this many mode solutions, we can definitely get a very stable operation. And so here is some early experiments to reach the stable operation through multi-mode solutions. But the problem with this one is also obvious. We can see the cavity length will be at a level of the meters. So we get a very large size in order to get stability. So this is not the solution we are looking for. And also another solution is use a single mode operation. Obviously, once you only have one mode, the laser operation will become much smaller. We have repeatedly said many times that if we add the filters into the optical cavity, we get a stable single mode operation. But here, actually, I would like to point another sense. If we just filter out all the wavelengths, left only one wavelength, we might not still get the single mode operations, because if we have a standard wave cavity structures, we'll have a standing wave pattern of optical field inside the cavity. So that means in some area, the optical field will be very large, and some area will be very small. So when you try to get the laser, some part of gain material will get consumed with other part of will less untouched. Some people say the mode computation for the laser is a kind of winner take all. But if you have this kind of so-called special whole body, then there's some region of the gain medium will not consumed, still leave room for other mode to get excited. So to completely eliminate the special whole body, what we do usually is add some oscillator. So makes this standing wave pattern and get rid of standing wave part, makes the operation like the traveling wave. So if we get the single mode operations, then we'll get a very stable laser performance. But the problem with this one for the display application is, once we get the single mode operations, the bandwidth of output laser beam will be very large. This light beam will be very coherent. Like we said, one big problem with laser display is we have a sparkle. This will kind of severely degrade the thing. Like the sparkle, we have more sparkle. So the single mode separation even can solve the stability problem, but kind of at the cost of the laser sparkle. So we are still trying to work out some few mode, multi-mode solutions. One way of doing this multi-mode solution is make use of the polarizations. When we discuss the laser mode, especially for longitudinal mode, the laser condition for longitudinal mode is after one trip of the travel, the light wave inside the cavity should repeat its phase. Then they can interfere with each other constructively. But another thing we didn't mention is we also require the polarization after one trip have to repeat itself. Otherwise, we cannot get the constructive interference. So this can be very easily achieved if the inside the cavity there is no Birefringent element. When we have a nonlinear optical crystal inside here, then only the light wave are polarized along this axis and this axis can repeat this polarization direction along after long trips. But if we add, quarter wavelength plates into the cavity, then this eigenstate of polarization will change from this orthogonal Ex and Ox will have a 45 degree in relationship with two axes. Then for these two modes, when they have a 45 degree angle with the axis, when we insert this type of mode into nonlinear optical crystals, this optical field can be decoupled along two components, one along EX, one along O axis. Same thing for the electrical field for the another frequency 2 or frequency 1 also can do the same thing. As when we have this two frequency and their polarization aligned like this, if you add this, there are some frequency mixing together, you will find that some frequency sum mixing will cancel each other. So as a result, the coupling between the frequency 1 and the frequency will be removed. So this green problem will go away. Another solution is just optimize the laser structure. People found under with some range of the parameters, because for this group problem, we always have spiky pulses. This spiky pulses will introduce more loss than we have a kind of quasi or continuous wave cases. So naturally, if we design the laser structure right, this spiky behavior will be disfavored. In the end, we can this SAVA, the continuous wave mode, will be favored. So by design optimize the laser structure, we can get a kind of so-called self-stabilized solution to get rid of the green problem. Of course, there are also some other solutions to these green problems. Here is one example again from Panasonic. This is their one setup based on the intracavity structures. Again, their nonlinear optical material is periodic polyethylene glyceride, and use ytterbium also validated as solid laser materials. The key feature for this one is they probably achieve the smallest size of the devices, just 2 cubic centimeter. This is the total size of the laser devices. The power level they have achieved 1.7. So if we can get these small devices, then to design the display system will be much better, and will so that display system itself will become much smaller. This is very good, but I doubt they are using this one as a kind of in their product. It's just the research result. This research result give us a kind of guidance, what kind of potential eventually we can achieve. But now, probably nobody can say thermally can manage such large heat with these small sizes. So we believe this is still a kind of research prototype, not the production structures. So far, we have kind of say discussed focused on the platform to generate the green light based on the frequency doubling. This technologies, compared to other platforms, is relatively mature and mature. But for us, at the beginning, we mentioned one of the obstacle for laser technology used in display technology, display application, is cost. The cost, because now you see for this kind of technology platform, we need a pumping structure, need a solid laser, need the nonlinear crystal. This structure is still very complicated, and these three different parts actually interact with each other. There are a lot of physics, and to make it really work, make the device really work, we actually in the practice we still need quite a few more components. The structure, in the end, we end up with a very complicated structure. If we have a very complicated structure, the device cost won't be cheap. So this is still a problem. And also, like I mentioned several times, the thermal management is still an issue. And so far, the component to make this frequency double lasers, and most of the expensive one is still pumping lasers. So this is still some issues with this technology platform. But this one is the most mature one. So most people still pursue this one, hope this one will be first to get commercialized. But compared to this one, actually there still are two competing technology platforms. One is the semiconductor laser. Like we said, this is the most simplest, straightforward one. Unfortunately, we have explained we cannot get efficient light emission from semiconductor material for green and blue, especially for green. Either because the material system, when they go to green wavelengths, they become indirect bandgap material, or when they go to green, the mismatch between the substrate and the epi layer become too huge, introduce a lot of defect, so the efficiency will be reduced. And also, this I would like to put this technology platform in a historical perspective. Like I said, repeatedly, semiconductor laser is a kind of first choice, at least the preferred choice for many applications. So if we can use the semiconductor laser, a lot of things will be much easier because it's small and cheap and very long life. Historically, we first get a semiconductor lasers right is for the 0.8 infrared semiconductor laser around the late 60s, early 70s. When we get the 0.8 micron wavelength semiconductor lasers mature, this technically mature, then we get the optical communication system. And after 10 years, more than 10 years, then we shift this wavelength from the 0.8 to 1.3 and 1.55, because that's the two windows for favorable for the optical fibers. And also, almost after 10 years, we get a breakthrough for the blue lasers. In the early 90s and the middle 90s, then Chia first made the semiconductor for blue. So you can see, now we have a red semiconductor laser mature. Almost every 10 years, we can work out one wavelength. So this one probably, we don't know exactly how long it will take, but for us, say if you want to get the say, if your time frame is say 3 years, you want to product, definitely this is not the technology platform you want to go. And also another one is a so-called upper-converging lasers. So I don't know, maybe you know one device is called Arvin doped optical fiber amplifier. This is a very important device for the optical communication systems. Some people say even without this Arvin doped amplifier, the whole internet as today is will collapse because of the Arvin doped amplifier. We can make the say wavelength WDM system possible. For this Arvin doped amplifier, we know it is its working wavelength is 1.5, but through upper conversion, it will generate some green light. And also for Arvin amplifier, because it's used as a backbone in a communication system, usually you use as say the undersea cables. 10 years ago, it happened. Some company sold this Arvin doped amplifier and installed underseas, but because of the upper conversion, they generate a lot of the green light. So this green light can coincident with some absorption spectrum with packaging material. So they kind of damage the package. So they have to record the material, record their say devices just say from the undersea. So this kind of very interesting episode. But now in the Arvin doped amplifier case, people is trying very hard to suppress the green light. Now people work at the same technology platform and other way around, try to enhance this upper conversion as much as possible. Now we can get over watts of output laser for this technology platform, but comparably, it's still not as good as we have discussed with this Friction technology problem. The problem with these upper conversion materials, they have to rely on the so-called cooperative upper conversion. What cooperative upper conversion means, for example, you have two electrons both on the excited energy levels. Then if these two electrons are close to each other, one electron might give up its energy, then go back to grounded state, transfer its energy to another electrons. So another electrons can further jump to a higher energy level. So this is we call the upper conversion. Because again, this is a process involving many particles. In principle, this many particle process, the efficiency may not as good like this say directly photon and electron process. So this is why this one of the reasons upper conversion lasers probably won't be as good as this Friction platform.
Other questions? Yes.
Just a question going back to the very start. You're talking about the generated versus the nonlinear effects. Is it possible to say much about the relative size of the nonlinear terms? You know, for example, the E squared term that's compared to the E term. I mean, it's usually okay, or in most circumstances, the E squared term is ignored. Well, what would the relative size of that term be? How do you know when you can ignore it and when you need to include it?
I think it's basically depending on the material structure, accessibility, the second order accessibility. In different material, we have different accessibility, second order accessibility. Some just almost close zero, some is high value for third order.
Yeah, so, I mean, typically what would that be? I mean, would that second order term be, so the chi, would it be 10% of chi 2 be 10% of chi 1 or 50%?
No, I think it is material dependent.
But, I mean, typically in these materials...
I'm not familiar with it. I just familiar with the material as it use a function doubling. I have no knowledge about the third order.
Okay. Good.
More questions? Yeah.
My question is on the practical side, like summary. For Raman spectroscopy studies, we currently use for the longer wavelengths, red lasers are usually all semiconductor diode lasers. On the other hand, when we go to green laser, it's argon ion laser is standard in the field. When we go to UV, we use frequency double argon ion laser, which is a pretty complicated device and expensive, and bulky, making analysis in field or in production difficult. I'm wondering if you envision that we may have a range of blue and UV semiconductor lasers that will have sufficient power to cover variety of spectroscopy needs in the near future.
Like I said, with a historical perspective, almost every year wavelengths we need 10 years to work out. But I think it's still possible because now a lot of people put a lot of effort to get this blue or green semiconductor lasers. For example, if we use gallium nitride material semiconductor compound to do that green, now the problem is because the mismatch between the epi layer and the substrate layers. Now people are trying to very hard to develop some material growth technology to grow some buffer. If they are successful, then this defect will be gone. Then we get this green laser.
Would you give a forecast? Is it within a couple of years, 5 years, 10 years, or
probably 5 to 10 years
after I retire?
Probably 5 to 10 years.
Thank you.
More questions? If not, let us thank the speaker again.